Okay, so now we have another law, but this says the limit of f to the n as x approaches a. We can basically take, so this is kind of a complicated problem because we're doing the limit of something kind of complicated, but this allows us to say, okay, you don't have to do all the complicated stuff with the limit. You can just do the limit of f and then do the complicated stuff afterwards. So it might make it easier. So in other words, an example of this is, suppose we had f of x equals x. So we could ask, what about the limit of x to the 10th as x goes to, say, 1? And this rule allows us to handle this by saying this is the limit of just x as x goes to 1, and then raise the whole thing to the 10th power. Okay? So we have that rule. Now let's talk about two more rules. So here we have two more rules, and these are very useful. So the first one says the limit of a constant as x approaches anything is just equal to the constant. So that is actually simple to understand. Suppose we have a constant. So our function here is the constant function. In other words, we're talking about some function equal to a constant function. So, for example, let's say this was equal to, let's suppose we had f of x equals 5. Okay, so let me make that 5. That's not very good. Try that again. 5. So we're talking about the constant function, which looks like that. Okay, so what does that mean? So the constant function does not have any x in it, right? It doesn't have x, doesn't have x squared, doesn't have any x. So it means it doesn't, the value is independent of x. So in other words, no matter what x you choose, it's always the same. It's always 5. So that's what we mean by a constant function. So f is always equal to 5, or the height is always equal to 5. So if we say, and suppose this is some a, and we ask what's the limit as x approaches a, the answer is 5. It's 5 everywhere, no matter what a, and the function is always 5. So we would say that the limit of this function here is as x approaches, let's make it concrete, let's say it's as x approaches 3, that's 5. But it doesn't mean just for 3, it's for any number. It's always 5. And if the constant is not 5, but some c, then the value is always going to be c. So that's what number 7 means. Okay? And the next one is also easy to understand. Number 8 says the limit as x approaches a of x equals a. Now sometimes that looks confusing because x doesn't look like it's a function, just like c didn't look like it was a function. But the function that we're talking about there is f of x equals x, or if you like, you can call that y. So the function we're talking about, for example, the graph is y equals x. In other words, it's just the 45-degree angle line. It's this. This is y equals x. So if we have that function, which is what we have here, and we ask what's the limit at some a, so if the x coordinate is a, the y coordinate is also a. So what's the limit? As x gets close to a, the height is getting close to a. So we have that the limit of x, the function x, as x approaches a, is a. So that's what this one says. That's what number 8 says. So now we can go back to that other question and say, what's the limit of x to the n as x approaches 3, for example. So how can we do that? So we can use this property here that says if we have something to the n, in this case we have x to the n, but whatever it is to the n, we can bring the n, the power, outside of the limit problem. So in this case, that means we can write this like this: the limit of x as x goes to 3, and then do the power later. So it makes the limit problem simpler to do. Instead of having to do something complicated, we have this, but we just learned how to do this. The limit of x as x goes to a is a, so the limit of x as x goes to 3 is 3. So inside the square brackets we get 3, and I didn't mean to do n. Let's say I wanted to make it more concrete. Let's suppose I did it, this was 5. Okay, so suppose we had that, then this is going to be 5, and so this is going to be 3 to the 5th. And so let's just write what we just wrote, what we just did. We said x to the 5th as x goes to 3. And we have that answer, and we get 3 to the 5th. Okay? So these rules, 1 through 8, make doing limit problems a lot easier. For example, suppose we had a polynomial, p of x, equal to, let's say, x to the 4th plus 2x squared plus 3x plus 1, and we want to know the limit of this polynomial as x goes to 2, for example, the limit of p of x. So we can use the rules. First of all, we can split this problem into one function plus another function plus another function plus another function, and so we can write this as the limit of x to the 4th. I'm going to leave out this 2 for the moment. I don't want to keep writing it. It has to be small. It's going to make it look messy. So it's supposed to be there, though. Plus the limit of 2x squared plus the limit of 3x plus the limit of 1. And all of these have the x. X goes to 2 here. I'm just not writing it. So now we know how to do this one. We just did one just like that. We just did this one. This was x to the 5th as x goes to 3. Now we have x to the 4th as x goes to 2. And we're going to get 2 to the 4th. So we know how to do that part. And then this part we know how to do because we said we can take the 2 outside. So we're going to get 2 times this limit without the 2. So the limit of x squared, again, as x goes to 2. So without the 2 there, it's the limit of x squared as x goes to 2. That's the same kind of problem as this was as well. So this is going to be 2 squared, right? And now we have 2 times 2 squared. And then this one, again, we can pull the 3 out because of one of our rules. And then we have the limit of x as x goes to 2. And we did that also. That was one of our, that was here. The limit of x as x goes to a is a. So the limit of x as x goes to 2 is 2. So we pulled out the 3. And then we got, well, I guess I'll write it out. And then here, this is the limit of a constant. That's just going to be the constant. So this is going to be what? This is going to be 3 times this thing is 2. So finally we just get an answer. What do we get? We get 16 plus 8 plus 6 plus 1. So whatever that is, that's the answer to this question. So whenever we have a polynomial, we can do some similar things. And in fact, you might see that what did we really do? We said the limit as x goes to 2, and we ended up just putting 2 into here, 2 into here, 2 into here, and then adding that 1 there. If you see, that's what we did. We've had x to the fourth became 2 to the fourth. The other one became 2 times 2x squared, 2 times 2x squared. Next one became 3 times 2, 3 times 2, here's the 2, and then plus 1. So without going through the proof of it, what we sort of have just shown is that the limit for any polynomial you can see that's going to be true for any polynomial, as x goes to any value, say a, not necessarily just 2, is that you can just drop in the 2 into each piece. So in other words, you can just put the a into p. So we can say that this is the result. So for any polynomial, we can do that because of all these rules that we have. All of these rule, this rule, and these rules. Okay, and then we have we've already shown this, or we've even shown more than that because we've shown for any polynomial. This is just in particular for x to the n. You can replace the x by the a, but we basically showed it for any polynomial, much more complicated than just simply x to the n. And this is basically, you can do the same thing for roots as well. So you can just replace the x by a again. It says if n is even, we assume that a is greater than 0 because we don't want to take square roots, for example, of negative numbers or fourth roots of negative numbers. Okay, and this is actually not just for x as the inside, but any function. Take the root of any function, you can just take the limit inside the nth root sign. So the limit now is inside the nth root sign. So it makes it a little bit easier because here we had to do the limit not just of f, but the nth root of f. That seems more complicated than just doing the limit of f, because the hard part of these problems is working with limits. So if we want to do a limit problem, we want to make that part as simple as possible. So here we have a more complicated limit problem than we do here. Here we only have the limit of f. Here we had to do the limit of the nth root of f. That seems more complicated than just the limit of f. And this rule says that we can switch like that. So we can move this nth root sign outside and take the nth root of the result instead of having to do the limit of the nth root, which would be harder. So going back to here, what we said about polynomials, we basically, we can say that we can just substitute in a into the polynomial. So directly substitute. So if you have the limit of a polynomial as x goes to a, you can just do direct substitution of a into the polynomial. And this actually works just as well if you have a rational function. So remember, what do we mean by a rational function? So let's say r of x is a rational function if it is can be expressed as the ratio of two polynomials. So it has to be expressed as the ratio of two polynomials. So for example, this is a rational function because it's the ratio of this and this. Both of these are polynomials. So this is a rational function. This r, let's call it r, is rational. However, I don't think that we could say that the sine of x is, sorry, this should be r of x. I don't think that we can say the sine of x is rational. I can't think of two polynomials that I can put one on here and one up here and one down here so that the sine of x equals that. So This is probably not a rational function. The sign is probably not rational. But this is a rational function. So going back to this direct substitution, even if p is not just a polynomial, but any rational function, we can do direct substitution. So for example, here we had x cubed minus 8 over x plus 7. Let's write that. So let's say we have r of x. I don't know why I want to write r of t. R of x is x cubed minus, I forget what I had there, x minus 8. Suppose we had that, and we want to know the limit as x goes to 2 of r of x. We can also just replace, even for a rational function, we can say the answer is going to be r of 2. Okay, so that's another limit. We also have that rule for limits. Now the only thing is, this works as long as 2 is in the domain of R. So what is not in the domain of R? So you can see from this that x equals 8 is not in the domain of R. So then we can't do that. So if we ask the limit as x goes to 8 of R of x, we can't do this substitution. Okay, so we can't say it's R of 8. I keep saying t. I don't know why I want to say t, but I mean that. So that's not. Okay, so this doesn't work necessarily. But as long as the number here that we're putting in is that we're approaching is not, I'm sorry, as long as it's in the domain, then this works also for rational functions. Okay, now we've been using this so-called theorem here, but we're stating it here. So it says that the general limit, remember this is the general limit, that's the general limit, and this is the right-handed limit, and this is the left-handed limit, and this is the right-handed limit. So this says that if the left-handed limit equals the right-handed limit, they're both equal to the same thing, then the general limit is also equal to that same thing. And also, if the general limit is equal to something, then both, this is the left-handed limit and the right-handed limit will both be equal to the same L. Okay? By the way, again, you see this if and only if that we've talked about before. And if we wanted to prove this, let's call this statement P, call that statement P, and let's call this statement Q. So what this is saying is P if and only if, that's how we can write if and only if, Q. And if you write that in English, I guess you would say P if and only if Q. And that is actually two statements. It's saying P if Q, that's one statement, and it's also saying P only if Q. Now, if you think about these, I'm not going to do it, I'm not going to try and talk about it, but if you think about that, this means P if Q is really saying if Q, then P, or in other words, Q arrow P. And then P only if Q is really saying, I guess, if P, then Q, or in other words, P arrow Q. So you have to think about this in English or in whatever language to see that that's what this or this means. So anyway, when we say P if and only if Q, we mean both of these, this and this. There's an and there. So it's both of these. So basically, if we want to prove this thing, P if and only if Q, we have to prove this, and we have to separately prove this. These are not contrapositives of each other, so we can't say once we prove this one that we prove this. We call these are converses of each other. Converses are not the same as each other logically. So if just because you prove one doesn't mean you prove the other. So what does this mean again? So we call this one P and this one Q. So like this one means what? If the left-handed limit is equal to the right-handed limit, then what? Then the general limit is equal to that same value. And this one says what? If the general limit is equal to L, then what? Then both the left-handed and the right-handed are equal to that L. Those are two separate statements. They both have to be proved. You can't prove one and say you prove the other. You have to prove both. So whenever you see if and only if, that means there are two statements being asserted and both have to be proved. So this is a theorem, means it has to be proved, but we're not going to prove it. But that's what it means. It means if Q then P and if P then Q. And sometimes we write it like this instead, P double arrow Q. Or sometimes we'll write it like this now. There's some difference between this single arrow and the double arrow, but I'm not thinking about that. So I might write it this way or I might write it this way, and they're both going to mean the same thing. Okay, so they both mean P if and only if Q. Okay, so anyway, we have this theorem. So we're going to assume that this is true without proving it. So with that in mind, let's consider this function. The absolute value function. So let's see if we can remember how that's defined. F of x is equal to, and it's actually defined piecewise. So if x is greater than, I guess it could be greater than or equal to or greater, you can put the equal sign either here or here. But anyway, if x is greater than or equal to 0, then we get x. And if x is less than 0, we get minus x, right? We talked about this before. That's the absolute value function defined as a piecewise function. So suppose we wanted to know what's the limit of this as x goes to 0. Suppose we wanted to know that. Now you probably know what the graph of this looks like. I guess I'll use this. That was not right. Try that again once more. That didn't work either. Okay, I won't use that. Someday. Okay, so it looks like this. Sorry, that was not good either. Okay, so you probably know that it looks like that, but let's do it with the aid of this theorem. So we want to know the limit of this function, the absolute value function, as x goes to 0. So if we want, we can do it this way. So if we show that the left-handed limit is equal to the right-handed limit, whatever that value is that it's equal to is also the limit of the general limit. So what does that mean here? What can we do? So we can do the left-handed limit. Let's say x approaches 0 from the left of the absolute value function. And there, whenever we're approaching 0 from the left, that means less than 0, then we get this. So we're doing this, equals the limit of minus x as x approaches 0 from the left. That's what we get. So Now what can we do? We can bring this outside. This is a negative multiplying by -1. Remember we said we're allowed to bring that outside. We can do -1 times the limit of x as x approaches 0 from the left, and that is -1 times 0 is 0. This part is 0 because we can put in the 0 into here. So we get -1 times 0, which is 0. And we can do the same exact thing. Well, no, sorry. We can say x 0 plus of the absolute value, and that is going to be the limit of x, because when x is positive, it's just x we need to work with. So that's x goes to 0 on the right, and that is also just going to be 0. So we've shown that the left-handed limit, and the right-handed limit are both 0. So going back up to that theorem, we showed that this and this are both 0. So that 0 is what the general limit is. So we've shown, which something that we could see if we think about the graph, and that is that the limit as x approaches 0 is 0 for this absolute value function. Okay, let's consider another function. Let's consider the limit of the absolute value of x over x as x goes to 0. Suppose you wanted to consider that. So let's try and show that the limit here does not exist. So why is that? First of all, let's just show it visually. So let's try and draw it. So when x is positive, what do we get? When x is positive, let's say put in 5, what do you get? You put 5, absolute value of 5 is 5, divided by 5 is 1. So when x is 5, you get 1. When x is 6, what do you get? Put in absolute value of 6 is 6, over 6 you get 1. When x is 2, what do you get? Absolute value of 2 is 2, over 2 is 1. So you get 1 everywhere. That's not very good, but let's say looks like this. Like that. Now, what about at 0, though? When x is 0, the absolute value of 0 is 0 over 0, so it's not defined there. So we need a circle there. We can't do that. Okay, now how about when x is -5? So -5, put -5 in here, what do you get? Get 5 over -5, so what is that? So 5 over -5 is -1. So if this is 5, get -1. Okay, let's try -4. Sorry, if this is -5. If this is -4, what do you get? -4 absolute value is 4 over -4. 4 over -4 is -1 again. What do you get when you put in -2? Absolute value of that is 2 over -2. You get -1 again. So what do you get? You get this. And again, you have to put a circle here. Okay, so that's the picture. So from the picture, we can see that as you get close to 0, the limit's not going to exist. But we want to be able to show that using the definition of the absolute value of x. and this theorem up here. So what we're going to do is we're going to look at the left-handed limit and the right-handed limit and show that they're not equal. So if we look at the left-handed limit, the limit absolute value of x over x as x approaches 0 from the left. So then the absolute value of such a number is going to be negative x. Sorry, I want to do this first. Undo that. It's going to be the limit as x goes to 0 from the left of negative x, right, over x. And that is we can bring the minus outside. We get this, the limit of x over x as x approaches 0 from the left. So this is 1. So that's the limit of a constant. So it's negative 1. So that is negative 1 from the left. And then I'll let you figure this part out. I think it's pretty clear. This is using the same kind of idea here. We're going to get that this is equal to 1. And so the left-handed limit is not equal to the right-handed limit at 0. One is negative 1, the other is 1. So the general limit does not exist. Okay, that is more or less everything we're going to say about limits. If we end up needing anything more about limits later in the course, we may come back and show a few more properties about limits. But for now, that's all we're going to say about limits.